Chapter 1. The Speed of Light. In complete darkness, under crushing pressure at the heart of our star, hydrogen nuclei fuse together. A photon is born. It will take thousands of years for this particle of light to fight its way through the dense solar plasma to the surface, and just 8 minutes to cross the vacuum and strike your retina. In that moment, your brain registers a flash. But physical reality is merciless. You are not seeing what is happening now. You are seeing a ghost. The event that created this light has long since become history, forever beyond your ability to intervene. This fundamental disconnect between reality and your perception is dictated by a single constant: the speed of light in a vacuum. We know this number with terrifying precision: 299792458 meters per second. Not 1 meter more, not 1 meter less. This isn't just a number on the universe's dashboard. It is the hard speed limit for transmitting any information whatsoever. Gravity, magnetic fields, even cause and effect. Everything bows to this strict limit. Look up at the moon on a clear night. To an observer, it appears as an unchanging companion, hanging in the sky right here and right now. But this is an illusion. Light takes 1.3 seconds to travel from the moon's craters to Earth's telescopes. When Soviet lunar rover operators sent a command, they had to wait almost 3 seconds for a response. We never see the moon in real time. We see it as it was just over a second ago. We're trapped in the past, even within our own cosmic backyard. Let's slow down here. If we lift our gaze higher, the scale of this delay becomes terrifying. Light from the Sunday takes 8 minutes and 20 seconds to reach Earth. If our star were to vanish right now, simply disappear from reality, we would continue basking in its warmth, and the planets would keep orbiting for more than 8 minutes. The gravitational field holding us in place also propagates at light speed. We live in ignorance of a catastrophe that may have already happened, but whose messenger hasn't yet reached our planet. But the solar system is just a tiny province. Consider the Andromeda Galaxy, the nearest major galaxy to us. That faint smudge of light, visible to the naked eye on a dark night. The photons now touching your retina left their stars 2.5 million years ago. At that time, modern humans didn't yet exist on Earth, and our distant ancestors were just learning to chip stones. When you look up at the night sky, you are not doing astronomy. You are doing archaeology. You are peering into the abyss of time. The cosmos we observe through telescopes like James Webb or Russia's Spectre. RG is a map of the past. Many of the bright giants we catalog today have already exploded as supernovae millions of years ago. But the news of their death is still en route. For us, they're alive. For the universe, they're dead. This concept of the light cone turns every observer into a prisoner of their own now, cut off from the true state of the rest of the universe by an impenetrable wall of space and time. All of our civilization, all of physics and philosophy, is built on the principle of causality. First cause, then effect. A broken cup doesn't reassemble itself. A bullet doesn't fly back into the barrel, and the guarantor of this order is precisely the finite nature of light speed. If signals could transmit instantaneously, the entire chronology of the universe would collapse into a single point. Past, present, and future would exist simultaneously. It is this delay, this pause at 300,000 kilometers per second, that gives time the ability to flow. But the human mind doesn't like accepting limitations. We've conquered sound, split the atom, reached orbit. It seems to us that the speed of light is just another technical barrier. Like the sound barrier, that needs to be overcome by building a more powerful engine. Engineers and science fiction writers have dreamed for decades of warp drives and hyperspace jumps. But Einstein's equations, verified by thousands of experiments, are unforgiving. The speed of light isn't the speed of matter's movement. It is the speed of reality's structure itself. Picture the horror of this situation. The faster you try to move, the slower time flows for you. If you attempt to chase a beam of light, you are not just accelerating through space, you are starting to deform the fabric of time itself. Overcoming this barrier means more than just getting from point A to point B faster. It means outrunning cause, seeing effect before the event occurs. This is a direct path to paradoxes, capable of destroying the logic of our existence. Modern science stands at a crossroads. On one hand, we have concrete data from experiments at the Large Hadron Collider, where we spend colossal energy accelerating protons to 99% of light speed, but never reach 100%. On the other hand, theoretical models allow for the existence of wormholes and space-warping bubbles. We're searching for a loophole in physics laws, hoping to deceive the jailer who has locked us in one star system. We begin our investigation with a question that may seem insane, but whose answer determines humanity's fate as a cosmic species. Is the speed of light merely a technical limitation, a set of numbers that can be hacked? Or is it the only fuse protecting the universe from complete chaos, where effect could kill its own cause? If we break this barrier, will reality itself survive? Chapter 2. The Accelerator. 299,792,458 m/s. For the theorists in our first chapter, this was a philosophical constant determining signal delay. But here, 100 meters underground in the concrete ring of a particle accelerator, this number feels completely different. This isn't just a figure. It is a challenge thrown at us by nature itself. The laser interferometry engineer working the night shift sees no romance in the starry sky. His reality consists of the hum of superconducting magnets cooled by liquid helium and graphs trembling on control room monitors. In this tunnel, we don't passively observe light. We try to race against it using the brute force of 21st century technology. The idea seems utterly simple, understandable to anyone who has ever driven a car. If you want to go faster, you press harder on the gas, burn more fuel, transfer more energy to the wheels, and the speedometer needle climbs upward. We transfer this logic to the subatomic level. We apply monstrous voltage, creating an electromagnetic field that should kick a proton and send it flying. In the initial stages, everything goes according to plan. We invest energy and speed increases. 50% of light speed, 80%, 90%. The counters flash. Recording acceleration, it seems like just a little more, one more powerful pulse. One more gigawatt of energy, and we'll break through this invisible ceiling. But right here, at the very finish line, familiar mechanics undergoes catastrophic breakdown. The engineer sees this in the energy consumption graphs. The power curve shoots vertically upward into the red zone, but particle velocity practically stops changing. We're burning energy capable of powering a small metropolis, but the speedometer needle seems to hit an infinitely elastic wall. Instead of accelerating, particles begin behaving anomalously. From the perspective of a high-energy physics specialist, something frightening is happening. The energy we're pumping into the system doesn't disappear. The law of energy conservation is immutable, but since it can no longer go into speed, it begins changing matter's very structure. A proton accelerated to near light speeds begins gaining weight. This phenomenon is called relativistic mass. The closer an object gets to light speed, the heavier it becomes for an external observer. This isn't an illusion or mathematical trick. The collider's magnets must generate increasingly powerful fields to keep these particles on trajectory. They're trying to turn a light proton but encountering the inertia of a heavy lead nucleus. In the Large Hadron Collider, according to recent experiments, protons accelerate to 99.9999% of light speed. We've approached the barrier so closely that we could seemingly reach out and touch the limit, but the price of these final percent is astronomical. At such speeds, each proton's mass increases 7,000 times compared to its rest mass. Think about this. We're trying to accelerate a speck of dust, but it transforms mid-flight into a boulder. All the energy that CERN's generators draw from France's and Switzerland's electrical grids now goes not into acceleration, but into feeding this monstrous mass. We've fallen into a perfect trap set by Einstein. Einstein's equation E equals mc works both ways. Kinetic energy condenses into mass, and the heavier an object becomes, the more energy is needed to accelerate it, even 1 more millimeter per second. This is a closed loop, a race impossible to win by simply raising the stakes. The mathematics of special relativity is absolutely ruthless here. In the denominator of the Lorentz formula sits a square root that approaches 0 as u near light speed. Any schoolchild knows you can't divide by 0. In the physical world, this means the energy curve goes to infinity to force any object possessing even the slightest rest mass, whether a proton, spaceship, or human. To reach full 100% light speed would require infinite energy. More than all stars in the universe have radiated throughout their entire existence. This isn't an engineering problem that can be solved by building a more powerful reactor. The engineer in the tunnel understands this better than anyone. When the magnet hum dies down after another experiment, the screens show the same result, 99.9%, but never 100 light speed. Isn't just a speeding ticket, it is an asymptote, a horizon line you can eternally approach, but never physically cross. So we find ourselves trapped. If our spaceship is made of matter, it can never move faster than a photon. We're doomed to crawl through cosmic emptiness, spending thousands of years traveling between stars. For human ambition, hungering to conquer the galaxy, this sounds like a sentence, life imprisonment in the solar system. But if we can't break through this wall with brute force, perhaps we're simply looking at the wall wrong. Physics prohibits matter from moving through space faster than light. But what if space itself is more complex than we're used to thinking? If you can't win on speed, maybe you need to change the rules of the game and examine the geometry of the prison itself. Chapter 3. The Geometry. The engineer in the collider tunnel sees an energy barrier before him, but the theorist in his office sees something different. For him, this wall that matter crashes into isn't built from joules and kilowatts, but from the very geometry of space. Sitting before a board covered in tensor calculus, he understands. We're trying not just to accelerate, but to hack the architectural blueprint of existence. The problem isn't the engine. The problem is the map we're traveling on. To understand this trap's nature, you need to stop thinking of light speed as a photon's movement through emptiness. In Hermann Minkowski's equations, which unified space and time into a single entity in the early 20th century, light speed isn't speed at all. It is an angle of inclination. It is the rigid framework, determining which events in the universe can be connected to each other and which will remain eternal strangers. Look at the visualization our theorist constructs. Every event, whether a supernova flash or your blink, is a point in four-dimensional space. From this point, up and down, spreads what physicists call the light cone. This isn't an abstraction, it is the boundaries of your reality. Everything inside the upper cone is your absolute future. These are the only places you can reach, and the only events you can influence. But the most frightening part lies not inside the cone, but outside it. Beyond these shining walls lies a vast portion of the universe that Minkowski called elsewhere, or somewhere out there. The mathematics here is unforgiving. Nothing happening in this zone can affect you now, and you can't affect it. There is no causal connection between you and these events. For an observer, this sounds like a death sentence. Most of the universe isn't just unreachable for us, it is causally severed. This is where we find the answer to the main question. Why does this limit exist at all? If signals could propagate instantaneously, the universe would turn into chaos, where everything happens simultaneously. Light speed is essentially the universe's refresh rate. It is the clock speed of the processor our world runs on. And this limit affects not only light, it controls the most powerful force known to humanity, gravity. Let's conduct a thought experiment that often haunts astrophysicists. Suppose someone could theoretically completely annihilate our Sunday right now. It simply disappears. What would happen on Earth at that exact moment? Intuition suggests that losing our gravitational center should cause our planet to immediately break from orbit and fly into the icy darkness of space. But relativity's equations tell a different story. For 8 minutes and 20 seconds after the star's disappearance, you wouldn't notice anything. Earth would continue orbiting around empty space. The gravitational well we're in cannot disappear faster than light reaches us. The fabric of space-time, warped by the Sunday's mass, would straighten out in a wave racing toward us at 299,792,458 m/s. You would see a Sunday that no longer exists. You would feel its warmth, and most amazingly, you would feel its gravitational pull. For those 8 minutes, Earth would be gravitationally interacting with a phantom, with the past. This proves that light speed isn't just a characteristic of photons. It is the fundamental speed of information transmission about where mass is located and how space should be curved. The theorist looks at his calculations and sees supreme harmony in this. Light speed limitation protects the principle of causality. Effect can never precede cause. First, the Sunday disappears, and only then, after a strictly allotted time, does Earth leave its orbit. If we could transmit signals faster than light, we would destroy this sequence. We could learn about the star's death before it died. Thus, the light cone isn't just a graph. It is the walls of our prison. We're trapped in the present, sliding into the future along these rays. We can't step sideways through the cone's wall because that would mean moving into elsewhere, which doesn't physically exist for us. The geometry of space-time forbids such trajectories as strictly as Euclidean geometry forbids triangles with 4 angles. The human mind poorly tolerates prohibitions. Looking at these perfectly drawn boundaries, the theorist begins searching for loopholes in the equations. After all, mathematics is a double-edged tool. It prohibits material bodies from moving faster than light inside ordinary space. But what does it say about what lies beyond the light cone's boundaries? Is this region empty, or is it inhabited by something we can barely imagine? If we accept that light speed is geometry, then the temptation arises to ask, can we change the topology? Can we, while staying inside our cone, Tilt the cone itself so our future intersects with someone's distant past. For the engineer, this sounds like nonsense, but for a space metrics specialist, this is quite a concrete task whose solution may be hidden in extreme states of matter. This geometric view of the world has frightening symmetry. If particles exist that, like us, are trapped inside the cone and move slower than light, then perhaps mirror reflections exist too. Particles for whom the light-speed barrier works from the other side. Particles born beyond our perception's edge in that very elsewhere. We call them tachyons. These are hypothetical wanderers for whom light speed isn't a ceiling, but a floor, the minimum possible velocity. In our theorists' equations, imaginary numbers begin appearing, describing these ghosts' mass. If they exist, then our entire orderly picture of causality, which we just constructed, could crumble in an instant, while we discuss the impossibility of overcoming the barrier. Mathematics whispers to us that the barrier might be one way, and if we can't accelerate to light speed to get outside, perhaps something from outside constantly bombards our reality, moving backward through time. Are we ready to look at formulas where mass becomes an imaginary quantity? Chapter 4. The Looking Glass. In the silence of the Theoretical Physics Institute office, the sound of chalk crumbling on the blackboard seems thunderously loud. For an outside observer, these symbols are just abstractions, but for the gravity theorist, they form a map of forbidden territory. We stopped at the light cone's boundary, calling everything beyond it elsewhere, where travel is forbidden. But special relativity equations, if examined carefully, contain no direct prohibition on life existing there. The problem we encountered earlier lay in mass. We discovered that accelerating ordinary matter to light speed makes its mass approach infinity, requiring infinite energy. This is a dead end. However, the theorist sees this not as the finale, but as just one side of the coin. He asks a bold question. What if objects exist that don't need acceleration? What if particles exist in the universe that are born already moving faster than light speed? To allow such a possibility, we'd have to commit violence against common sense and introduce the concept of imaginary mass into the equation. In school algebra, we learn that you can't extract the square root of a negative number. But here, on this board, the imaginary unit is the key unlocking the door to Wonderland. If you substitute imaginary mass into Einstein's formulas, the mathematical prohibition disappears. The solution becomes real, but the physical meaning turns inside out. These hypothetical particles, which physicists named tachyons from the Greek word tachys, fast, aren't just quick particles. They're the fundamental antipodes of our world. For you and me, light speed is an unreachable ceiling, a hard upper limit. For a tachyon, light speed is a solid floor, a lower limit. It is physically incapable of moving slower than 299,792,458 m/s. Imagine a world where all thermodynamics works backward. The theorist observes with horror and delight as equations describe this looking glass wanderer's behavior. When an ordinary object loses energy, it slows down. We're used to this. Friction and medium resistance dampen velocity. But a tachyon, when it loses energy, begins to accelerate. The less strength it has, the faster it flies through space. This sounds like a paradox, but mathematics is unforgiving. If a tachyon lost all its energy, its speed would become infinite. It would exist at all points of its trajectory simultaneously. Conversely, to slow down a tachyon, you must pump it with energy. To decelerate it to light speed would require, just like in our case, an infinite amount of energy. The light-speed wall stands firmly, but it works both ways. We're trapped inside. In the world of slow speeds that physicists call tardionic, tachyons, if they exist, are trapped outside. We can never cross paths. The light-speed barrier separates us more reliably than the thickest prison wall. The chalk's tapping on the board stops. The theorist steps back, trying to comprehend this isolation scale. Two worlds overlaid on each other, but never touching. However, the mere possibility of tachyon existence has haunted researchers for more than half a century. If we could interact with them, if we could catch even one such ghost, it would overturn our understanding of reality. After all, an object moving faster than light inevitably violates time's familiar flow. For some observer, a tachyon might arrive at a detector before it was emitted from its source. I want you to grasp the full depth of this problem. We're not just talking about speed of movement through space. We're talking about destroying causal connections. If tachyons are real and capable of carrying information, then we could send a message to the past. You could receive an answer to a question you haven't yet asked. This isn't just science fiction. This is a direct conclusion from the equations drawn before us now. This is precisely why most physicists, including our theorist, approach tachyons with skepticism. Nature typically punishes cruelly for attempts to violate causality logic. Either tachyons don't exist at all, being merely a mathematical curiosity, or they exist but interact with ordinary matter, not at all. They might pass through Earth, through these laboratory walls, and through you and me right now, remaining invisible. Nevertheless, the hunt for them has continued. Scientists have tried detecting them through Cherenkov radiation, special luminescence that occurs when a particle moves in a medium faster than light, propagates in that medium, but the vacuum remains silent. No experiment at accelerators or in cosmic rays has provided confirmation of their existence. Detector graphs remain clean, leaving tachyons to live only in chalk dust on university blackboards. This universe's silence might be salvific. If we discovered particles with imaginary mass, we'd have to rewrite not only physics textbooks, but the philosophy of existence. Vacuum stability would be under threat. Quantum field theory predicts that tachyon birth could lead to so-called tachyonic condensation, a process capable of changing our universe's fundamental constants. For the theorist, this equation with an imaginary unit remains a reminder of our ignorance. We've built a magnificent model of the world, but it is full of blank spots. Mathematics permits what intuition prohibits. We're searching for escape from the light prison, and tachyons are a tantalizing hint that life exists beyond the wall, even if that life is completely alien and unreachable to us. But if we can't become tachyons, if we can't turn our mass into an imaginary quantity without destroying ourselves, then this path is closed. We can't break through the wall head, and we can't outrace light by competing with it in speed. This is a race that matter loses by definition, so we need to stop thinking about movement through space. The theorist's gaze slides from special relativity formulas to the more cumbersome equations of gravity. If you can't move faster than light inside space, perhaps you should make space itself move. After all, unlike you and me, the universe's fabric itself isn't subject to Einstein's limitations. And here, in curvature geometry, hides the next, even more insane hope. Chapter 5. The Warp Drive. If we can't accelerate matter to light speed without violating fundamental conservation laws, then the entire problem formulation was wrong. We were trying to win a race where defeat was predetermined, fighting growing mass and vacuum resistance. But Einstein's equations contain a loophole hinted at by the expanding universe's very existence. The speed limitation of 299,792,458 m per s only applies to objects moving through space. However, this prohibition doesn't extend to space itself. On the computer simulation screen, we see not a familiar rocket flight with roaring nozzles, but something fundamentally different. The ship hangs motionless at the center of a three-dimensional coordinate grid. Stars around it don't blur into lines from acceleration. Instead, the space grid itself begins behaving like a fluid. The geometry in front of the ship's nose contracts, pulling distant objects closer, while behind it rapidly expands, pushing the traveled path backward. This isn't movement in the classical sense. This is manipulation of reality's metric. In 1994, Mexican theoretical physicist Miguel Alcubierre proposed a mathematical solution that transformed this visual effect from science fiction into rigorous physical modeling. Inspired by Star Trek, he asked whether it is possible to create a configuration of matter and energy that would locally curve spacetime exactly this way. His paper, published in Classical and Quantum Gravity, proved that general relativity doesn't prohibit creating such a bubble. Alcubierre's metric essence involves forming a wave, like disturbance in the spacetime fabric. Imagine a surfer in the ocean. The surfer himself can stand on his board completely motionless, making no effort, but the wave beneath him races toward shore at tremendous speed. In this model, our spaceship is the surfer. It exists inside a flat, uncurved region of space, a sort of storm's eye, safely protected from external chaos by the bubble's walls. Inside this bubble, the ship's speed relative to surrounding space strictly equals zero. This is a critically important point, solving the problem we encountered in the second chapter. Since local speed equals zero, the ship's relativistic mass doesn't increase. The crew doesn't need infinite energy for acceleration, because technically they're not accelerating anywhere. They simply hang in vacuum, waiting for arrival, while space itself carries them to their destination. Moreover, being inside the Alcubierre bubble removes the overload problem. In a classical ship, the acceleration necessary to achieve near light speeds in reasonable time would flatten pilots into biomass. But here the free-fall principle works. Gravitational forces arising from space curvature compensate each other inside the bubble. A pilot could hold a hot coffee cup, and not a drop would spill, even if the bubble maneuvered or braked with thousands of G's acceleration. For external observers remaining on Earth, such a bubble would look like an object moving at faster than light speed. It could cover the distance to Proxima Centauri in days or even hours, overtaking light photons emitted at launch. This seems paradoxical, but physics knows precedence. During the cosmological inflation epoch, immediately after the Big Bang, our universe's space itself expanded faster than light speed, advancing the boundaries of creation. The Alcubierre drive is an attempt to reproduce this cosmological process on a local scale. The visualization demonstrates this disturbance's structure. In front, space compresses, reducing the distance to the destination point. Kilometers become meters. Behind, space expands, creating new distance between the ship and launch point. The ship doesn't overcome distance in the familiar sense. It destroys it in front and recreates it behind. We seemingly fold the carpet path in front of us to instantly find ourselves at the other end. However, this model generates unique optical and radiation effects. At the bubble's forward boundary, where space is extremely compressed, photons flying toward us would shift into the hard gamma range. For an observer inside the bubble, the universe ahead would become a blinding point of deadly radiation without protection. Behind, the event horizon would be absolutely black, as light trying to catch the bubble simply couldn't overcome the expansion zone. In this silence, inside the bubble, the time dilation problem is also solved. In special relativity, the faster you move, the slower time flows for you. Returning from near-light speed flight, an astronaut would discover that centuries had passed on Earth. But in the Alcubierre metric, since the ship's local speed equals 0, no time dilation effect occurs. Clocks on board and clocks at Earth's mission control would run synchronously. The pilot wouldn't lose touch with his era. This elegant solution bypasses Einstein's famous prohibition without violating its letter, but violating its spirit. Light still remains the fastest object moving inside space. But the bubble itself, being a separate fragment of geometry, falls outside this jurisdiction. We're not overtaking light on the track. We're taking a piece of track with us and moving it faster than any race car can drive on it. Alcubierre's theoretical model became the first serious argument that interstellar travel doesn't necessarily have to last millennia. It moved the discussion from the plane of "this is impossible" to the plane of "this is an engineering task." On theorists' monitors, the equation converges. The metric tensor obediently describes the required curvature. It seemed we'd found the key to the prison, and the path to the stars was open. But as soon as we transition from pure geometry to physical reality, the price of this ticket emerges. Einstein's equation links space curvature to matter and energy. To curve space as strongly as the warp drive requires, we need colossal gravitational influence. In nature, gravity is created by mass. The greater the mass, the stronger the curvature. But the warp bubble needs not just mass. Analysis of the energy momentum tensor in Alcubierre's model shows frightening numbers. To create a bubble with a radius of just a few meters, capable of carrying a small probe, requires energy density comparable to the mass of the entire observable universe. This was the first blow critics dealt to the theory in the 90s. It seemed the idea was dead. What is the point of an engine whose fuel tank should be larger than the entire cosmos? However, science doesn't stand still. Over the decades that followed, theorists like Chris van den Broek found ways to optimize the bubble's shape, making its walls thinner and the curvature itself more efficient. Today, in 2025, optimized models have reduced the warp drive's energy appetite from universe scale to a single gas giant planet. Look at this visualization. On one side of cosmic scales sits your tiny ship, on the other, Jupiter. To start the engine, you need to convert into pure energy, a mass on the order of 1.9 Fin 10 Fe kilograms. This is Jupiter's mass entirely, down to the last hydrogen atom in its atmosphere. The engineer looks at this hypothetical balance with cold skepticism. According to Einstein's formula, E equals mc Fe, converting even a gram of matter produces a colossal explosion. And here we're talking about a planet. If we could instantly annihilate Jupiter, the released energy would burn the entire solar system. To say we've reduced requirements to planetary scale is like rejoicing that, to boil a teapot, you now need not the entire sundae, but only a medium-power nuclear explosion. This is still beyond our technologies. But let's suppose for a moment that we're a Type 3 civilization by the Kardashev scale and know how to juggle stellar energies. Even in this case, we face a problem not of quantity, but quality. This is the deepest mystery of warp mechanics. Gravity, as we know, and observe it through telescopes, always works through attraction. Ordinary matter, whether rock, planet, or black hole, always has positive energy density. It bends space beneath itself, creating gravitational funnels where everything rolls in. For the warp drive, one gravitational well isn't enough. Remember the bubble structure. In front, space compresses, but behind it must expand, pushing the ship forward. To force space to swell and expand locally, you need something acting opposite to gravity. You need anti-gravity. For this, the field equations dictate a harsh condition. The energy density in the bubble's rear part must be less than zero. This isn't just vacuum. It is a state emptier than absolute emptiness. Here physics enters the territory of so-called exotic matter. It is important not to confuse it with antimatter. Antimatter that we obtain in accelerators has positive mass and positive energy. It just has opposite electric charge. It falls downward like an ordinary stone. Exotic matter with negative mass is something fundamentally different. If you had a ball of such substance, it would weigh -5 kilograms. And this births paradoxes that give classical mechanics migraines. Tree-imagining interaction with a negative mass object. Newton's second law says force equals mass times acceleration. If mass is negative, then when applying force, the acceleration vector changes sign. Simply put, if you push such a ball away from you, it won't fly forward. It will fly at you. If you try to stop it, it will accelerate. This is substance that behaves contrary to all our intuition, but it is precisely what is necessary to stabilize the warp bubble's throat. Without exotic matter creating negative pressure on space's fabric, any warp bubble would collapse instantly, transforming into a black hole along with the ship inside. The laser interferometry engineer knows we've never observed anything like this in the macro world. We've studied millions of stars, galaxies, and nebulae. Everywhere our gaze reaches, mass is positive, gravity attracts. The universe seems monotonously normal in this aspect. It appears nature has imposed a ban on negative energy's existence in free form. This creates what engineers call the unobtainium problem. We have blueprints for a starship capable of conquering the galaxy. We have flawless mathematics describing its flight. But we don't have the material from which to build the engine. This is like Leonardo da Vinci having perfect jet aircraft blueprints, but only wood and canvas as available materials. We stand before a locked door whose key perhaps wasn't even provided by the universe's architect. However, before closing the warp drive project and declaring it unscientific fantasy, we should look deeper, where classical laws stop working and intuition loses meaning. If we don't find negative energy in the cosmos of giant planets and stars, perhaps we're searching at the wrong scale. What if the answer is hidden not in Jupiter's enormous masses, but in the microscopic whisper of vacuum itself? In the quantum mechanics world, the concept of emptiness has a completely different meaning. Quantum field theory hints that vacuum's energy balance doesn't necessarily equal absolute zero. Conditions exist where local energy can drop below the baseline of calm space. This sounds like violating thermodynamics laws, like a free lunch. But physicists know one phenomenon proving negative pressure is real. It is not in a distant galaxy, it is right here in our laboratories. But to see it, we need to turn our gaze from stars and look at two tiny metal plates. Chapter 6. The Casimir Effect. The search for exotic matter moves us from astrophysicists' offices to sterile nanotechnology clean rooms. We're not looking for a new planet, but for a quantum effect that could become the spark for a warp engine. If we can't find negative mass in nature, Perhaps we can create conditions where vacuum itself begins behaving like exotic matter. This is our only chance to deceive gravity. In the underground laboratory, the laser interferometry engineer peers into a vacuum chamber. For an ordinary person, there's nothing inside this chamber, absolute emptiness. But for the engineer whose eyes are accustomed to quantum fluctuation graphs, emptiness doesn't exist. He knows that nothing is the most boiling and unstable substance in the universe. The main question of this chapter sounds like a paradox. Can emptiness possess force? Intuition tells us vacuum is the absence of everything, zero, and zero can't push, pull, or press. However, quantum electrodynamics equations assert the opposite. If we're right, then space's fabric itself possesses hidden pressure that can be used. And if we learn to manipulate this pressure, then the warp drive key is in our pocket. But first, we need to make emptiness work. The engineer focuses attention on the experiment's heart. Two thinnest gold-plated plates hang suspended in the vacuum chamber's center. They're electrically neutral. Between them are no charges, no magnetic fields. According to Newton's classical physics, these plates should hang motionless for an entire eternity. But sensors register the impossible. The plates begin slowly but inexorably approaching each other. Some invisible hand is squeezing them. This isn't gravity. It is too weak at such scales. This is vacuum's breath itself. To understand this force's nature, we need to accept that vacuum isn't empty. Heisenberg's uncertainty principle prohibits the existence of fields with absolutely zero energy. Space boils with so-called virtual particles. They're born in pairs, live for an infinitesimal fraction of a second, and immediately annihilate. This is quantum foam that bubbles everywhere, in space, in your room, and right now, between these golden plates. Virtual particles behave like waves of all possible lengths. Outside the plates, in open space, rages a storm of waves of any size, from microscopic to gigantic. But in the narrow gap between mirrors, the situation is different. Only those waves whose length is a multiple of the distance between plates can fit there. Long waves simply don't fit in this slot, like an ocean wave can't enter a narrow bathtub. This creates a fundamental imbalance. The engineer sees this imbalance's result on the monitor. Pressure outside turns out higher than pressure inside. From outside, all types of quantum waves beat against the plates, while inside only short ones are permitted by the gap's geometry. External vacuum literally pushes the mirrors into each other. This phenomenon was predicted by Dutch physicist Hendrik Casimir in 1948, but confirming it with high precision was only achieved at the turn of the 21st century. Here lies the solution to warp drive fuel. Inside the gap, vacuum's energy density is less than outside. If we take external emptiness energy as zero, then energy between plates becomes negative. The Casimir effect is the only laboratory, confirmed proof of negative pressure existence. We've found that very exotic matter. It didn't arrive from another galaxy. It was always here, hidden in empty space's properties. This discovery causes mixed feelings in the engineer. Triumph and disappointment simultaneously. On one hand, physics doesn't prohibit negative energy. Here it is, recorded by instruments. So, the Alcubierre bubble is theoretically possible. We're not violating nature's laws when we ask space to expand behind the ship due to negative energy density. The universe knows this trick. But looking at the numbers, the engineer understands the monstrous complexity of scaling. The Casimir force is only felt at distances of several nanometers. If you spread the plates, even by a micron, the effect disappears, pressure equalizes. To create a negative energy zone sufficient to cover a starship, we'd have to surround it with a shell having structural density comparable to a neutron star, or create gaps thinner than an atom around the hull's entire perimeter. Current technology doesn't allow creating macroscopic Casimir vacuum. We get cruel irony. Nature showed us that negative energy exists, but locked it in nanoscale. The energy density we obtain in the Casimir effect is infinitesimal for curving spacetime around a ship. For the warp drive to work, we need energy equivalent to Jupiter's mass, but with a minus sign. And we can barely scrape together energy capable of attracting a dust particle. The gap between theory and practice spans dozens of orders of magnitude. The engineer turns off the installation. The plate freezes. He understands. We can't take this effect with us. We can't build an engine that will generate sufficient negative energy aboard a flying ship. This is a dead end for the autonomous starship concept. If we want to travel faster than light, we'll have to abandon the idea of carrying the engine with us. Perhaps the curvature structure itself needs to be created, not on the ship, but laid out in space beforehand. We're approaching a paradigm shift. If the Alcubierre bubble requires impossible amounts of onboard fuel, then maybe we should consider external propulsion. Imagine not a ship that punches its own way through, but a pre-built tunnel where negative pressure conditions are maintained by stationary generators of colossal power. We're transitioning from the automobile idea to the railroad idea. Instead of trying to change physics around a small ship, we can try changing space's topology along the entire route. This returns us to the work of Russian theoretical physicists from the 90s. They proposed a solution that removes the need to carry negative mass Jupiter with you. But this solution has its own price. You can't fly where you haven't already been. In the next chapter, we'll leave the nanotechnology laboratory and return to star maps. We'll examine the concept of the Krasnikov tube, a structure allowing faster than light travel without violating local physics laws. This is cosmic subway that might become our only ticket to the stars, but which conceals an even more frightening threat to causality than simple warp drive. Chapter 7. The Krasnikov Tube. We leave the sterile laboratory with its nanometer gaps and return to where scale matters. Abandoning the idea of carrying the engine with us changes the entire philosophy of interstellar flights. If we can't compress space around the ship using onboard installation, then we'll have to change space's structure itself, cutting a permanent corridor through it. This is the transition from lone sailboat tactics to transcontinental highway construction strategy. For the gravity theorist standing before a board with metric equations, the universe stops being an empty stage. It becomes deformable material. In 1995, Russian physicist Sergei Vladimirovich Krasnikov, working at Pulkovo Observatory in St. Petersburg, proposed an elegant solution to the Alcubierre problem. He understood that a bubble requiring Jupiter's energy was a dead end. But what if the ship's trail doesn't disappear, but remains in space-time fabric forever? The scientist's gaze slides across the chalk diagram where a straight line between Earth and a distant star transforms into a complex topological fold. This is the Krasnikov tube. Unlike the warp bubble, which needs continuous feeding, the tube is a stationary distortion of space-time metric. You don't fly faster than light in the familiar sense. You move inside an artificially created channel where the very concepts of distance and time are changed once and forever. The main paradox of this technology, which the theorist sees in formulas, lies in the inevitability of the first step. You can't create a tube faster than you are capable of moving yourself. To lay this cosmic subway to Alpha Centauri, the first builder ship must make the journey at ordinary sub-light speed. The crew will age 4 years, laying rails through vacuum. Instant transportation miracle won't happen for the pioneers. However, for everyone who follows them, the game rules change. The Krasnikov tube possesses a property that frightens even hardened astrophysicists. When returning through this tunnel, time flows differently for the traveler than for external observers. If the ship flies inside the tube, it moves along a geodesic line, allowing it to return to Earth practically at the same moment it arrived at the star by outside observer clocks. Mathematics here is merciless. Inside the tube, the space-time interval is constructed so the light cone, that very prison bars of causality, tilts. This allows the ship to move in one direction at a speed that appears infinite to the external world. But unlike the Alcubierre bubble, here there is no frontal shock wave of radiation, and negative energy requirements, though remaining colossal, become a construction problem rather than a flight problem. For our theorist scribbling Greek symbols on the board, this concept looks like an engineering blueprint, not fantasy. Tube walls must be held from collapse by that very exotic matter we sought in the previous chapter. But now we don't need to generate it on the fly. We can theoretically reinforce the tunnel with rings of negative energy density substance, creating stable structure for millennia. But precisely here, at the junction of engineering genius and fundamental physics, a frightening anomaly arises. Sergei Krasnikov showed in his works that one tube is safe for causality. You can fly far and fast, but you can't return earlier than you departed. However, if you build a second tube, a return path laid toward the first, the system becomes something more than just a transport hub. The theorist circles a closed loop on the diagram with chalk. This is the moment of truth. The combination of two Krasnikov tubes directed in different directions is mathematically equivalent to creating a time machine. If you fly through one tube there, then through another back, equations permit a situation where you return to Earth before your departure moment. Interstellar travel infrastructure inevitably becomes a tool for violating chronology. This discovery puts us before a harsh choice. Either light speed really is an absolute limit that can't be bypassed even with geometric tricks, or the universe permits the existence of temporal loops. The Krasnikov tube isn't just a way to reach the stars. It is a loophole in reality's defenses, allowing history to be rewritten. If physics permits such a solution, then somewhere in Einstein's equations hides a self-destruction mechanism of logic. We look at the galaxy map, and route lines now seem like scars on time's body. Perhaps civilizations reaching this level don't just travel through space, but exist outside linear time. But while this is just dry numbers on a chalkboard, to understand whether such distortion is possible in reality, we need to stop drawing formulas and try to hear how space itself groans under stress. All theoretical models, both the Alcubierre bubble and Krasnikov tubes and wormholes, rest on one fundamental postulate: space-time is flexible. It can stretch, compress, and vibrate. For a long time, this was just a beautiful hypothesis, an axiom on paper. Physicists lacked the most important thing: experimental confirmation that reality's fabric is actually capable of trembling. We leave the theorist's quiet office. Chalk dust falls to the floor, leaving formulas unsolved. The answer to the warp drive reality question doesn't lie in equations, but in gigantic engineering structures built to catch the universe's whisper. To build a tube to the stars, we must first prove that space isn't emptiness, but a physical object that can be struck like a bell. In the next chapter, we'll go to a place where we learned to listen to this trembling. We'll see how black hole mergers billions of light, years away, force mirrors on Earth to shift by distances smaller than an atomic nucleus diameter. This will be the ultimate proof. Our universe isn't a rigid box, but a moving, living membrane ready for manipulation. Chapter 8. Hearing the Universe. We leave behind dusty boards with unsolved equations and move from mathematical abstractions to reality's cold concrete. The theory that space can be twisted into tubes or inflated into bubbles remains beautiful fantasy until we get confirmation of this medium's main property. To build a road to the stars, we must be certain that the road itself, space-time, is actually capable of bending under external influence. For a long time, physicists considered space just a passive stage, a rigid framework on which matter's drama unfolds. If this framework is static, then no warp drive is possible in principle, no matter how much energy you invest. But now we're in a place built with one goal: to catch the universe's trembling itself. This is the LIGO gravitational wave detector, and here decides the fate of interstellar travel. Deep at night, the laser interferometry engineer walks along a 4-kilometer vacuum tube. For him, this structure isn't just the world's most expensive vacuum, but a gigantic seismograph of reality. His work involves paranoid struggle with noise, a passing truck in a neighboring state, ocean surf hundreds of kilometers away, even atomic thermal motion in mirrors. All these enemies can mimic a signal from distant space. The experiment's essence is brilliantly simple and terrifyingly complex in implementation. A powerful laser beam splits in two and travels down perpendicular tunnels. If space is absolutely rigid and motionless, both beams will return and perfectly cancel each other out, leaving darkness on the detector. But if space-time compresses or stretches even a fraction, the laser paths become different, and light appears at the output. The 14th of September, 2015, after decades of tuning, this perfect darkness on monitors changed to a meaningful signal. The engineer sees on screen a characteristic burst that came simultaneously to detectors in Louisiana and Washington. This wasn't equipment failure or Earth's seismic activity. A gravitational wave passed through our planet, not noticing its matter. The source of this disturbance was 1.3 billion light years away. Two black holes, each about 30 solar masses, circled in a death dance, approaching each other. In the final fractions of a second before merger, they accelerated to half-light speed, whipping space-time fabric like a mixer whips cream. At the moment of collision, energy was released that is monstrous even by astrophysics standards. For tenths of a second, mass equivalent to 3 of our suns converted to gravitational waves. For this brief instant, this event's radiated power exceeded the power of all stars in all galaxies of the visible universe combined. And this wasn't light. This was pure deformation of geometry. But most amazing is what reached Earth. The engineer looks at displacement data and sees a number hard to comprehend. The gravitational wave stretched and compressed the detector's 4-kilometer arms by a distance equal to 1/1000th of a proton's diameter. Tree grasping this precision, it is like measuring distance to the nearest star accurate to a human hair's thickness. This microscopic trembling became monumental proof. Space isn't emptiness or abstraction. It is a physical, elastic medium. It behaves like a tightly stretched drum membrane. If you hit it hard enough, a wave travels. And if a medium can transmit waves, then it yields to manipulation. We got the answer to the main question. Reality's fabric is indeed elastic. Scientists converted gravitational wave frequency oscillations to the audible range, and the world heard the so-called chirp, a short sound like bird chirping, sharply rising to high frequencies. For the engineer, this sound is more important than Beethoven's symphony. It is the sound of an event horizon collapsing. The first time humanity heard space rather than saw it. For our goal, creating a warp drive, this discovery is the cornerstone. Now we know for certain that the Alcubierre metric and Krasnikov tubes don't contradict the nature of existence's fabric itself. Space can be compressed and stretched. Problems move from the physically impossible category to the incredibly technically difficult category. However, this experiment also showed the frightening scale of necessary efforts. To cause oscillations the size of a nuclear fraction required the energy of merging black holes. Nature seems to mock us. Yes, space is flexible, but its rigidity is colossal. To curve it strongly enough to create a warp bubble around a ship, we'd need energies that gods, not engineers, operate with. We proved space can vibrate, but vibration is a linear process, just light ripples on an ocean surface. To travel faster than light, we need not just to send ripples, but to roll this ocean into a tube or punch a hole through it. Gravitational waves confirmed flexibility, but they also hinted at matter's extreme states, where two black holes merged into one, space curvature reached infinity. At this point, familiar physics laws break down, and reality's fabric might not just stretch, but tear, connecting distant points. We've approached the very edge of understanding the universe's structure. If space can be deformed so strongly, is it possible to create a shortcut through it? The hum in the engineer's headphones dies down, but data on screens continue streaming. We've confirmed reality is plastic. Now we must learn what happens when this plasticity is pushed to its absolute limit. In the next chapter, we'll peer into places where space closes in on itself, forming bridges capable of connecting not only different map points, but different eras. Chapter 9. The Wormhole. The space-time ripple we detected with LIGO told us about the universe's flexibility. But these waves are just echoes of catastrophe that occurred billions of years ago. Here, in the high-altitude observatory where air is so thin that every breath takes effort, our astrophysicist searches not for echoes, but for the source itself. He peers into sky regions that seem to contain nothing but darkness. But precisely in this darkness hides the answer to the question, what happens when reality's fabric is stretched to its limit and tears? We're used to considering black holes dead ends of stellar evolution, cosmic graveyards where matter compresses into a point of infinite density, a singularity. But Einstein's general relativity equations allow for another solution. The astrophysicist sees on monitors not just a gravitational funnel, but a structure that doesn't end at the bottom. Mathematics suggests the funnel might have a continuation, transforming into a tunnel connecting two distant regions of space. This hypothetical tunnel was described in the 1930s by Albert Einstein and Nathan Rosen, calling it a bridge. However, the more capacious name given by American theoretical physicist John Wheeler in 1957 stuck in science. He used the analogy of a worm eating a path through an apple to get to the other side faster than crawling over the surface. Thus the term wormhole was born. For observers in the observatory, a wormhole isn't just a geometric abstraction, but a potential shortcut through the universe. If such an object existed, It would look like a spherical mirror reflecting light from another galaxy. Stepping into this sphere here, you would instantly emerge thousands of light years from Earth. This sounds like the perfect solution to interstellar travel problems, but physics always presents its bill. The main problem with wormholes is their monstrous instability. Calculations show that the Einstein-Rosen bridge is dynamic. It opens and closes so fast that even light can't pass through it. The tunnel throat collapses under its own gravity's action faster than you can take a step, turning any traveler into an energy clot inside the singularity. To transform this death trap into a passable highway, we again need what so frightens classical physics, exotic matter, that very substance with negative energy density, whose traces we sought in the Casimir effect. Only by filling the wormhole's throat with this anti-gravitational concrete can we create repulsive forces that will keep tunnel walls from collapsing. Suppose an engineering civilization of the future solved this task. We have a stable wormhole. One entrance mouth is in Earth orbit, the other near Proxima Centauri. You enter the airlock, and a second later find yourself in another star system. Space is conquered. But precisely at this moment of triumph, the astrophysicist realizes we've opened Pandora's box, far more terrible than simple distance. The thing is, a wormhole connects 2 points of space-time, and the key word here is time. Wormhole mouths are physical objects. They have mass and obey special relativity laws. This means if we start moving one of the mouths, the same thing will happen to it as to any fast-moving object. Time will slow down for it. Imagine we leave one wormhole mouth on Earth and load the second onto a starship. The ship accelerates to near light speed, makes a journey, and returns. Remember the twin paradox. For the ship's crew, say, a year passed, while on Earth 10 years flew by. But here is the catch. The clocks inside the wormhole itself, connecting the two mouths, remain synchronized. You stand on Earth next to the returned ship. The calendar shows 2035. But if you look into the wormhole mouth that is aboard the ship, you'll see Earth circa 2026. The entrance and exit are now separated, not by distance, but by time. The tunnel through space has become a tunnel through history. This is an inevitable consequence of relativistic mechanics. Moving one tunnel end relative to the other creates a time difference between entrance and exit. If you enter the ship's end of the wormhole, you'll instantly find yourself at Earth's end. But 9 years before you took the step, you'll exit into your own past. From the astrophysicist's perspective, looking at cold stars, this discovery changes everything. We were searching for a way to outrun light to conquer the galaxy, but we found a way to break causality. The wormhole is a natural time machine, and once we allow the possibility of returning to the past, physics stops being a set of equations and becomes a catastrophe scenario. If you can return to the past, you can meet yourself before departure. You can prevent your own start. You can kill your grandfather. The logical structure of the universe, where cause always precedes effect, begins cracking at the seams. We stand at the threshold of paradoxes that could destroy reality's very fabric. In the next chapter, we'll see what happens when a closed, time-like curve allows effect to cancel its cause. We'll learn why the universe may have a built-in protection mechanism against such violators, and how nature itself rebels against you, changing your yesterday. Chapter 10. The Grandfather Paradox. The discovery we made at the wormhole's throat frightens with its inevitability. We're used to thinking that space and time are different entities, but for the gravity theorist standing before a chalk-covered board, they're woven into a single monolith. The equations leave no room for hope. Any attempt to deceive space by moving tunnel mouths automatically becomes an attempt to deceive time. This isn't a side effect of engineering error. This is a fundamental law written on existence's framework itself. In the office silence, broken only by chalk scraping, the gravity theorist draws a simple line on Minkowski's diagram. This is a world line, an object's path through history. While your speed is less than light speed, this line points upward toward the future, staying within the light cone's safe boundaries. But as soon as we allow faster, than light travel, the chalk sharply veers sideways. The line breaks through the cone's protective shell and invades the forbidden zone that physicists call space-like region. The main question that has tormented physicists for centuries sounds like this: can you move faster than light without violating chronology? Intuitively, you want to answer yes. It seems to us that time is an absolute river flowing the same for everyone. But special relativity destroyed this illusion back in 1905. The concept of now doesn't exist on a universal scale. What is happening now for you may be deep past or distant future for a moving observer. Look at the problem through our theorist's eyes. He sees not just a graph, but a map of reality. The plane of simultaneity is a time slice you consider the present moment. But this slice's angle depends on your speed. The faster you move, the more your simultaneity plane tilts relative to fixed stars. And if you overcome the light speed barrier, this tilt becomes so critical that your movement vector begins pointing into mathematical yesterday. Here Lorentz's ruthless geometry comes into play. Imagine you send a faster than light signal from Earth to a distant ship moving away from us at near light speed in your reference frame. The signal flies into the future. But for the ship's crew, whose simultaneity plane is warped by monstrous speed, this signal arrives from the future into the past. Mathematics here is unambiguous. A reference frame exists where message reception occurs before its transmission. On the board appears a diagram known as the tachyonic antitelephone. This is a thought experiment that turns the warp drive dream into a logical nightmare. If you can instantly move to point B, then change reference frames and instantly return to point A, you'll return before you left. Space-time geometry closes in a loop. You are not just outrunning light. You are outrunning the cause that generated your movement. For the gravity theorist, this isn't a philosophical paradox, but a collapse of the entire physical model. All science builds on the causality principle. First, you pull the trigger. Only then does the bullet fly out. First, the glass falls. Only then do fragments scatter. This order is the cement holding reality's bricks together, but faster. Then, light travel changes equation signs. Time intervals become negative. Effect begins preceding cause. Imagine an observer's horror as he records instrument data. He sees the target explode into splinters a second before the shooter raises his weapon. Glass shards gather together and fly onto the table an instant before someone knocked them over. In a world where movement faster than light is permitted, such absurd scenarios become physically acceptable. Causality stops being a rigid rule and becomes just a recommendation easily violated. Many warp drive enthusiasts try ignoring this fact, hoping for some loophole. They speak of absolute time or preferred reference frames. But the theorist knows experiments don't lie. We've verified relativistic time dilation on GPS satellites and in particle accelerators. Space-time structure is unified. If you allow movement from point A to point B faster than a photon can do it, you inevitably open the door for time travel. The computer screen simulates a situation with two faster-than-light ships. They exchange signals due to simultaneity relativity. The second ship's response to the first ship arrives an hour before the first sent its request. The first ship's captain receives an answer to a question he hasn't even formulated yet. Now he can decide not to send the message at all. But then where did the answer come from? The logical chain breaks and reality begins collapsing. This phenomenon is called causal violation or chronoplasm. If information can get into the past, then the future stops being a consequence of the present. It begins forming itself. We get closed, time-like curves where events become the cause of themselves. The theorist looks at the equation and understands. The universe can't allow such anarchy. Either light speed is insurmountable, or our understanding of logic is fundamentally wrong. Thus, light speed isn't just a speedometer limitation set by the universe's traffic police. It is a protection mechanism. It is the wall separating an orderly sequence of events from chaos where past, present, and future mix into a meaningless cocktail. Overcoming this barrier means hacking reality's operating system and getting administrator rights we're not ready for. We've approached the most dangerous line of our investigation. If faster than light travel is possible, then time travel is possible. And if time travel is possible, then a paradox arises capable of driving any logician insane. You can return to yesterday and prevent today's departure. But if you didn't leave, how did you return to stop yourself? This closed circle is called the grandfather paradox. The theorist erases complex graphs from the board, leaving only one simple loop. The timeline curves and bites its own tail. In the next chapter, we'll see how the universe reacts to such insolence. We'll learn why a pistol aimed at the past always misfires, and how probability itself changes to protect history from your interference. Physics prepares us one last, strangest surprise. Chapter 11. The universe fights back. You stand before your ancestor. In your hands is a loaded weapon, in your head the determination to test reality's strength. You press the trigger. Silence, misfire. You work the bolt, aim again. But at this moment, slip on the smooth floor. The bullet goes wild, shattering a vase behind the unsuspecting person's back. This looks like a series of ridiculous accidents, like a bad comedy script. But for the theoretical physicist, there is nothing funny here. This is the work of a fundamental law of history conservation. We're used to thinking the past is a fragile porcelain figurine. One clumsy movement, and it shatters to pieces, changing the future beyond recognition. However, general relativity equations paint a completely different picture. The universe isn't fragile glass, but a viscous, self-healing polymer. Attempting to change the past encounters resistance from space-time fabric itself. The more persistently you try to create a paradox, the more harshly reality will correct your actions so the result remains unchanged. In the mid-80s, outstanding Soviet astrophysicist Igor Dmitryevich Novikov formulated a principle that today bears his name, the Novikov self-consistency principle. He asked a simple but frightening question. What if the probability of an event that could change history physically equals zero? This isn't a philosophical prohibition, but a strict mathematical limitation. The universe allows time machine existence, but it categorically prohibits paradoxes. To understand Novikov's logic, look at the situation through a ballistics expert's eyes. Imagine a billiard ball that flies into a wormhole, moves to the past, and emerges from another mouth to hit itself and prevent its entry into the wormhole. This is a classic paradox. If it prevents itself from entering, it won't exit from the exit. The self-consistency principle states, the ball will indeed emerge from the past, but at precisely such an angle to hit its younger version, and it is this hit that will push it into the wormhole. We get a closed loop. The hit from the past doesn't prevent the ball's entry into the time machine. It becomes the cause of this entry. This is a closed time-like curve. In this geometry, there is no concept of changing the past. You can't kill your grandfather because you are already alive. The fact that you exist is 100% proof that all your attempts in the past already failed. You are just playing a role written for you at the universe's birth moment, for an observer inside such a time loop. This sounds like a death sentence to free will. If Novikov's principle is correct, then inside a temporal loop, you become a marionette. You can want to pull the trigger. You can plan this for years. But at the decisive moment, quantum fluctuation will burn your pistol's firing pin, or a heart attack will knock you off your feet. Physics will find a way to preserve the causal fabric intact, even if it has to kill the traveler. Igor Novikov and his colleagues, including Kip Thorne, analyzed these scenarios with frightening detail. They concluded that physics laws near closed time curves work, so that paradoxical outcome probabilities always approach zero. This is like energy conservation law, except instead of joules, the universe conserves events, logical sequence. You can be a participant in past events, but not their editor. However, this principle births another, no less disturbing phenomenon, the ontological paradox, or bootstrap paradox. Imagine you travel to the past and give young Albert Einstein a ready manuscript of general relativity. He publishes it under his name. You learned this theory from his books. Question: who authored the theory? Information exists in a loop. It has no beginning and no creator. It simply is. For classical science, accustomed to seeking first causes, this is a real nightmare. Novikov's self-consistency principle solves the grandfather paradox problem, but makes reality's structure frighteningly deterministic. If we allow wormhole existence and warp drives, we must accept that the future already exists as really as the past. All of universe history is a single four-dimensional crystal frozen in eternity. We only slide our consciousness along its facets, mistakenly believing we're making decisions. But even if Igor Novikov is right, and paradoxes are impossible, a purely technical problem remains. Creating conditions for time travel requires monstrous energies. We're talking about twisting space-time into a donut. And here, quantum mechanics enters the scene, which, unlike relativity, doesn't tolerate such geometric abuse. Quantum fields behave extremely aggressively in closed time loops. Imagine a photon entering a time machine. It flies to the past, travels the same path, and again enters the time machine, meeting itself. Now there are 2 in the next cycle, 4, then 8. Since a time loop allows particles to return infinitely, many times to the same instant, energy density at the time machine's event horizon begins growing exponentially. This process, the very moment an engineer presses the on button on history's first time machine. Vacuum inside the device boils. Virtual particles circulating in a closed trajectory accumulate infinite energy in zero time. This phenomenon is called vacuum feedback, like a microphone beginning to squeal if brought too close to a speaker. Space-time begins resonating with itself until it self-destructs. This brings us to a hypothesis that might bury all our dreams of conquering time. If Novikov's principle protects history's logic, then quantum physics seems to protect chronology's very structure by destroying any mechanism capable of violating it. Perhaps a time machine is a device that always explodes a nanosecond before its first launch. We find ourselves in a strange situation. Einstein's relativity allows time loops and offers geometric solutions like wormholes. Novikov's principle reassures us that there will be no paradoxes. But quantum field theory screams that attempting to create such a loop will lead to catastrophe. This is a conflict between humanity's two greatest theories, and it happens right at the time machine's threshold. Stephen Hawking, studying these processes, put forward the chronology protection hypothesis. He argued that physics laws are arranged to make time travel impossible for macroscopic objects. It seems there is a chronology protection agency that makes the universe safe for historians, he joked. But behind this joke hides deep physical truth. Reality's stability requires sacrifices. And this sacrifice is our ability to freely move through time. Thus, the pistol aimed at grandfather misfires. Not because of magic. It misfires because the probability of successful shot in a closed time loop is suppressed by all of quantum statistics' power. And if you try to bypass this by building a more powerful machine, you'll simply provoke the tunnel's collapse. Space would rather destroy itself than let you create a logical error in existence's code. Chapter 12. Quantum Entanglement. The Last Hope. Novikov's self-consistency principle, which we discussed earlier, saves logic by preventing paradoxes. But it doesn't save the engineer. The gravity theorist, looking at quantum field equations, sees in them not just a mathematical prohibition, but a physical death sentence. If the universe can't stop you through circumstances, jammed trigger, slippery floor, or heart attack, it resorts to weapons of mass destruction. We descend to reality's most fundamental level, into the boiling ocean of quantum foam. Here, at Planck-length scales, emptiness doesn't exist. Vacuum is filled with virtual particles that are born in pairs, annihilate, and disappear in an instant. In ordinary space, this process is chaotic and safe. But inside a time machine, or closed time-like curve, these harmless fluctuations become executioners. Look at the catastrophe mechanism through a physicist's eyes. As soon as you create a tunnel to the past, for example with a wormhole, you create a path not only for yourself but for light, radiation, and virtual particles. A photon entering the tunnel mouth exits in the past, flies to the entrance, and again dives in to travel this circle once more. It becomes its own double. Unlike a billiard ball that can hit itself only once, quantum field completes infinite cycles almost instantly. This phenomenon physicists call vacuum feedback. The effect is frighteningly similar to what happens when you bring a microphone too close to a speaker. The audio signal loops, amplifies, and becomes unbearable squealing. Only here, instead of sound, vacuum energy itself resonates. Since particles return to the past, they overlay themselves before they even manage to leave the source. Energy at the time machine's event horizon begins growing exponentially. In fractions of nanoseconds, energy density approaches infinity. This isn't just equipment failure. It is local space-time collapse. This very effect underlies Stephen Hawking's famous chronology protection hypothesis, formulated in 1992. Studying field behavior in curved space, he concluded that physics laws conspire to prevent macroscopic objects from time traveling. Nature hates time loops as much as it hates perpetual motion machines. For observers, this looks like cruel irony. Einstein's general relativity, The gravity theory kindly allows us to build geometric structures for time travel. It provides blueprints, but quantum field theory, matter science, burns these blueprints along with the laboratory the moment we press the start button. This is a conflict between modern physics' two pillars that happens at the time machine's threshold. Hawking expressed this thought with characteristic English humor. It seems there exists a chronology protection agency that makes the universe safe for historians. But behind the joke lies cold calculation. Quantum fluctuation divergence at the Cauchy horizon is a mathematical wall we don't yet know how to break. Any attempt to stabilize the passage requires negative energy, but it is precisely this that provokes quantum instability. This mechanism explains the famous Fermi paradox in time context. Where are all the tourists from the future? If time travel were possible, our era would already swarm with observers with cameras wanting to film World War I/II's beginning or Mars landing. Their absence is perhaps the most weighty experimental proof of Hawking's hypothesis. We don't see future guests, not because we don't interest them, and not because they observe some non-interference code. We don't see them because the door they're trying to open is mined by reality's structure itself. The moment civilization reaches technology levels allowing temporal loop closure, the device destroys itself. However, science doesn't stand still. Some modern string theory calculations hint that under certain conditions, for example using supersymmetric particles, quantum resonance might not be so destructive. But this requires energy and conditions unachievable, even for Type II Kardashev scale civilization. For us 21st century humans, the prohibition remains in effect. The theorist in his office sets down the chalk. Equations on the board lead to a disappointing conclusion. We're trapped in the present, not because of our engine's imperfection, but because of the universe's fundamental architecture. Light speed and time's unidirectionality are existence's load-bearing structures. Attempting to remove this brick brings down the entire building. Thus, we come to understand that time isn't just a coordinate you can stroll back and forth on like a park path. Time has an immune system, and this system works flawlessly. Quantum vacuum stands guard over causality, guaranteeing that cause will always precede effect, no matter how hard we try to cheat the system. But if transferring matter and humans through time causes such violent vacuum reaction, perhaps there is a loophole for something less material. What if we abandon the idea of sending an astronaut to the past and try sending pure information? A bit of data, a warning, a signal. This brings us to physicists, dreamers' last hope, quantum entanglement, a phenomenon Einstein called spooky action at a distance. If we can't overcome light speed physically, can we do it informationally, using quantum world's strange laws where space seemingly doesn't matter at all? After the theoretical crash we suffered in the previous chapter, silence settles in the laboratory. Hawking's chronology protection hypothesis made it clear. Attempting to push matter through a time loop ends in catastrophe. Vacuum burns bridges. But the engineering mind always seeks workarounds. If massive matter causes such universe fury, perhaps we can deceive the system by abandoning mass. What if we send not an astronaut or even a microchip, but something weightless, pure information? Look at this optical table through a laser interferometry engineer's eyes. Here are no massive magnets or roaring turbines. Just quiet cooling system hum and thinnest optical fiber threads. We enter the quantum mechanics realm, the only physics section that seems to ignore common sense. Here we try using a phenomenon that Albert Einstein dismissively but warily called spooky action at a distance. We're talking about quantum entanglement. The experiment's essence looks deceptively simple. We take a source that births a photon pair and separate them. One stays here in Earth's laboratory, the other goes, say, to a module in Mars' orbit. The distance between them is millions of kilometers, according to quantum mechanics laws. These two photons aren't two different objects, but a single system described by one wave function. They're connected by an invisible umbilical cord that doesn't break, no matter how far we separate them. The engineer on Earth conducts a measurement. He checks spin, a quantum characteristic of rotation, of his photon. Suppose the device shows spin up. At the same instant, without any delay, the Mars photon acquires spin down state. This happens not in the 3 minutes light requires, not in a second. This happens instantly. Zero delay. Space between particles seems to stop existing. This seems like communication's holy grail. If state change happens faster than light speed, then we found a loophole. We can build a quantum telegraph transmitting messages to the galaxy's other end in real time. You press a button on Earth, and a light bulb lights up on Alpha Centauri. Goodbye, universe loneliness. Goodbye, light barrier. However, when the engineer begins analyzing data, euphoria changes to cold understanding of cosmic censorship's genius. The problem lies in quantum measurement's very nature. When you measure your photon's spin, the result comes out absolutely randomly. This is pure lottery. 50% probability spin will be up, and 50% that it is down. You can't force your photon to take the state you need. You can't order it to become a 1 or 0 to encode useful information. You are just an observer recording nature's random choice. Yes, your colleague on Mars will instantly get the opposite result. If you got heads, he'll definitely get tails. Correlation is 100% and instant. But what does the Martian observer see? He sees the same random noise sequence. He doesn't know you measured something. For him, it is just chaotic spin succession carrying no meaning. He has no way to distinguish spontaneous state appearance from your measurement result. To turn this quantum connection into a message, you must call your colleague and say, "Hey, I just measured photon number 1, and I got spin up." Only then will he understand that his spin down isn't chance, but the second half of your measurement. But to transmit this instruction, this cipher key, you must use an ordinary classical communication channel, radio waves, laser. And they, as we know, fly at light speed. This is the fundamental limitation known as the no-cloning theorem and no-communication theorem. Nature allows universe parts to be closely connected, feeling each other instantly at any distance. But it categorically prohibits using this connection to transmit orders. You can possess a common secret with a particle at the universe's edge, but you can't use this secret to change the past or outrun time. The engineer looks at correlation graphs with bitter irony. This is like nature's perfect crime. Evidence is obvious, instant interaction really exists. They gave a Nobel Prize for this in 2022, but causality isn't violated by an iota information. Useful, structured information capable of affecting events still crawls across the universe at 299,792,458 m/s. Quantum teleportation really allows transferring one particle's state to another. But this isn't matter teleportation like in fantasy films, not thought teleportation. This is statistics transfer that becomes understandable only after classical confirmation receipt. Lightspeed acts here not as jailer, but as strict notary, without whose seal no deal in the universe is considered valid. Thus, even at reality's deepest quantum level, we find no holes in the fence. Entanglement binds space into unity, making the universe whole, but it doesn't give us time machine keys. We can see event shadows happening instantly, but to comprehend them, we need time. The light barrier withstood attack from energy side, geometry side, and information side. We've exhausted all physics, known ways of cheating, from super-powerful accelerators to wormholes, from warp drives to quantum paradoxes. Every time it seemed we'd found an exit, the universe gently but persistently returned us to the same constant. It seems time has come to stop fighting this limit and try understanding why it exists at all and what would happen to us if it didn't exist. Chapter 13. The Final Answer. We've traveled a long path from the solar core to black hole event horizons, from quantum foam to observable universe boundaries. And now, as we mentally rise above the ecliptic plane, leaving Earth to shrink to a pale blue dot, it is time to admit defeat, or perhaps the most important victory in knowledge's history. Throughout this entire film, we tried hacking reality's code, searched for loopholes in Einstein's equations, built hypothetical warp drives, and drilled wormholes. We behaved like prisoners tapping cell walls seeking voids. But the universe answered us with silence. We sought ways to move faster, but each time hit not technical obstacles but fundamental logic laws. Now, gazing at this magnificent galactic web, we understand. Light speed isn't photon movement speed at all. It is our reality's processor clock frequency. It is the maximum speed at which cause can generate effect. If we could overcome this barrier, we wouldn't just find ourselves at another star. We would destroy the very before and after structure on which our existence depends. At our investigation's beginning, we asked, is 299,792,458 m per s a prison wall? The answer we received frightens and delights simultaneously. This isn't a wall, it is a load-bearing structure. Without this limitation, the universe would collapse into chaotic state where all events occur simultaneously, where thermal death arrives at the Big Bang moment, and gravity instantly tears apart any structures. Light speed limitation is the only reason you exist and have time. To realize this fact, we're used to thinking the cosmos is huge and empty. Distance between stars is a curse isolating civilizations. But look at this differently. Precisely light speed's finiteness turns space into a gigantic archive. Looking through the James Webb Telescope, we see not distant rocks, but living history. We see galaxies as they were 13.8 billion years ago. If light propagated instantly, the night sky would be blindingly white, burning retinas, and the past would disappear irretrievably the same second it occurred. The light barrier preserves the universe's memory for us. Great Russian thinker Konstantin Eduardovich Tsiolkovsky said Earth is the cradle of reason, but one cannot live in a cradle forever. However, physics dictates harsh conditions for growing up. Perhaps we're never destined to personally shake hands with representatives of other civilizations somewhere in the Andromeda Nebula. Entropy and space-time geometry seemingly prohibit creating galactic empires as science fiction portrays them. We're separated, not by kilometers, but by years. And this quarantine might be the only thing saving us from the dark forest hypothesis and instant destruction by more advanced neighbors. But in this limitation lies our greatness too. We're trapped in the present moment, sliding along the razor's edge between absolute past and unreachable future. Yet our mind can model processes occurring at the universe's other end. We learn to feel space-time ripples born from black hole mergers billions of years before the solar system appeared. We can't outrun light with our bodies, but we long ago outran it with thought. The paradox is that the prison whose walls we so fiercely tried to destroy turned out to be the coziest and safest home, specially built for life's emergence. Our path to understanding nature's fundamental laws is never straight. We often seek complex workarounds where we simply need to accept the game rules. Exploring the possible's boundaries is what makes us human. This matters more than it sounds. If you, like us, feel this sacred awe before creation's scales and want to continue seeking answers to physics questions, stay with us. Your attention and support is the energy allowing us to continue this infinite journey to the event horizon. Light speed isn't a limit. It is a horizon. And horizons, as we know, have the property of receding as we approach them. We remain here on Earth, but our gaze is fixed on infinity. We can't violate causality, but we can fill our allotted time with meaning. And while a photon born in a distant galaxy flies through emptiness for millions of years to touch your eye, remember, this delay is life itself. The universe isn't silent. It just speaks very, very slowly so we can hear it. We're no longer prisoners, we're time's guardians.